Okay, so hi, welcome everyone. So my name is Olivia Quinet. I work at Clupons inside the R&D department. And I'm in charge of industrializing the statistical method developed by our scientists before putting them in C++ production-ready code. So Clupon is specialized into providing software that detects error mistakes in medical trials. So our main customer are the pharmaceutical companies. The pharmaceutical companies conduct clinical trials in which they assess the safety, the security, the efficiency of their drugs on patients before submitting all these results to the FDA, for example, in the States, or the EMA in Europe, before commercializing the drug. So it's very important that they do not have errors and mistakes in their data, their supporting data. So when I say error and mistake, it's because we are human, and of course humans, we made errors, for example, by not following properly the clinical protocol. When we take measure, or the measurement is faulty, or we don't report the data correctly into the form or in the electronic system, and we have Clupon is providing statistical methods to detect this type of errors so that pharmaceutical company can take action and, for example, send investigator on site, so in the hospital that took the measurement and take some corrective action. So that's for the broad introduction. So the title is Applying Modern C++ Efficient Expression Evaluator with Type-erasure, but I should have corrected to apply contemporary C++. Same type, and the trick is with a small object optimization to obtain efficiency, but that was a bit too long. So the agenda of this talk is the motivation. Why do we need an expression evaluator in our work? Then I will go with some definition and state the scope of this talk. Then I will show you a naive approach for an expression evaluator and some benchmark. And then I will introduce the type-erasure with the small object optimization, do some more benchmark, and show that in this case, we can reach, but not quite reach, the performance of direct C++ expression evaluation, so the compile expression. We can reach the same timing. And then I will finish by what I learned during this project, and finally by some question, if you have any. And I really hope that you will have questions. So, yes. So motivation, as I said, so we deal with clinical data. And so those clinical data are most of the time stored in tabular format. The problem is that all the data stored in those datasets is very dependent on the sponsor, or even for the same sponsor, we have different format depending if the measurement was, for example, done by a lab or a CT scan or with a doctor. So everything is a bit different, and there is no, I would say, harmonized view of the data. So we need to harmonize the data. And so for this, sometimes, most of the time, we need to create, for example, new columns. Here, for example, we created 2 columns, CP center and CP patient. So which is just to retrieve, in this case, the identifiant for the center, so for example, the hospital, and the identifiant for the patient within the study. So we need to split, for example, here, simple, the sub-ID column into 2 parts. Left part is the site, right part is the patient ID. But of course, we have different formats, and sometimes we have to do even much more complicated operation to retrieve these quantities, which is sad, but that's life. sometimes we also have to extract data. So for example, we need to extract the visit date, so the date at which the patient has come to the hospital. And we also need to know if the visit was performed, because sometimes you have, if the visit is performed, you have in that data set the actual visit date, which is interesting. But you also have the planned visit date for the future, but we need to know if the patient came to that visit or not. So there's a lot of things that can be done. And sometimes also we have to split data set. For example, here the data set is split into two arms. Arms in the clinical data, it's a subset of patients, which they differ most of the time by the protocol. So they follow slightly different protocols so that the pharmaceutical company can study the effect, for example, of dosage of a medication on the clinical response. So, in summary, we need to deal with evaluation of user-defined expression on clinical dataset, and those expressions can be very different, and we need to deal with different type of data. And also, this evaluation needs to be quite efficient, because those datasets can be quite huge, sometimes bigger than millions of rows, and it's normal to have sometimes hundreds of those datasets. So you don't want this to be slow, because of course we have a lot of customers, and so we don't want them to fight for CPU time. We want them to have a product that is reactive. And we need flexibility. So as I said, we need to support different data types and different type of function that can help the user with their expression. And also, we would like the user to receive a meaningful error message in case of mistakes in their expression. So yes, there are other expression evaluators available, but they are mostly focused on just mathematical expression like XPRTK, XPREval, and so on. The other way would be, for example, to go with interpreted language like Python or SAS code. And that's what is currently done. And so the user has to enter all the code, run it, and then after the run, they get a feedback if there is an error, if everything works fine. But it's very difficult for them to debug and see what's inside, because otherwise it's like giving them too much freedom inside the machine, and we don't want that. So a bit of definition. So for example, let's take the expression 3 times a plus 2 in parentheses. I hope you can see it clearly. So that's a string of characters. So that string is passed to a Lexer tokenizer, which creates a vector of tokens. So for this, for example, we have first a literal 3, then the multiplication operator, left parenthesis, a variable a, the plus operator, the literal 2, and the right parenthesis. And this vector of tokens is then passed to the parser, which creates the abstract syntax tree. So, and at the root node will be the mul with, on the left-hand side, the literal, and the right-hand side, the plus with, again, left-hand side variable, right-hand side, the literal 2. And we also need a context. A context will contain some constant like pi, but here it's not really useful for clinical data, but it might contain also all the value of the variable reference into the expression. And also it can contain predefined function, for example, for transforming quantities from one unit to another unit. For example, if you take the temperature of a patient, you want it not in Fahrenheit, but in degrees, so that the whole data set has value in degrees. So it's better to do this transformation before applying some statistical test. And I say temperature, but there is measurement for the eighth, so you have inches, centimeters, meter. For the weights, even worse. And for dates also, because you have American dates and everything, and you have to standardize everything. So, yes, in this talk I will focus not on the lexer or the parser, but really on the nodes, because that is what is important. We want to evaluate a node for example, 1 million times on a dataset. So I will focus on the node. And a naive approach to implement those nodes is the object-oriented, of course. So you have a base class called est node with virtual function eval that return a result. And you define derived classes for each type of node that you have. So here for the expression, you have a literal, a variable. So literal will simply contain the value. Variable will contain the name of the variable plus a pointer to the context. For the plus and the multiply, you will have a pointer to the left and right-hand side node. So in your code, more or less, you have something like this. You define a p node as a static unique pointer to the base class. Same for the context, and the result will be, for example, a stud variant of the different possible value that you have to handle. So you create the context with all the value, you create a parser with the context, then you have your root node at line 7, you set the context, you obtain the result, and the answer should be 42. So, and for example, the implementation of the plus node, so constructors just take a left and right side node. The eval, you first have to, of course, evaluate the left node and then the right node. Then you combine the two of them with stud visit because we are dealing with variant. So it combines all the possible value of left and right. So you define the operation that you want to support in the compute struct. And here, for example, we support between long and double, and for everything else, we don't support. And give you the right result. Yes. So with the OO approach, the memory is more or less this. So you have a pointer to the context in the heap. You parse your nodes, so you have your root nodes to multiply. You have a lot of dependencies. It's just what I said before, but it's maybe a bit more visual here. And so when you call eval on the root node, so there is quite a lot of cost associated to it. You have to access the heap object through a smart pointer. Then you have to access the eval of that object via the VTVL. So there is two indirection already. Then you have to call stud visit. And then you create a stud variant. And this is for all the nodes inside your expression. So if you do some benchmark, of course, that reflects badly on the benchmark because it's about, just for this expression, the object-oriented method is about 7 times slower than the direct C++ evaluation. And for example, another library, expert-tk, it's more or less the same time as the C++ expression. So there is room for improvement, clearly. So of course, if you have more complex expression, the factor just increase because you have more and more interaction in your evaluation. So can we do better? So I try to answer this question with the type erasure design pattern because it's something I really like. It's You deal with value, you don't deal with pointer directly in your code, so it's cleaner. And so I will this is a few slides to summarize what is this design. So the type-erasure design pattern provide a value semantic interface, so with a fixed set of methods to manipulate unrelated types, open set of types. So example that is well known, and if you saw the talk of Klaus this morning, is again the shape. So you have you can define three shapes: a circle, a square, a rectangle, and you can draw them. But everything is value semantic. So for the user, there is no dynamic allocation, at least visible. So the problem is that we have quite a lot of boilerplate, so that is a summary. So we have the public shape object with a pimple inside. You have a constructor that just creates the pimple. You have the interface draw that we call doDraw of the pimple. So the pimple is use the base class shape concept. Shape concept is kind of a virtual interface structure with a virtual destructor and all the methods you want to apply to your value. And in the shape model, you actually store the shape. And you just call the free function draw on the shape for each type of shape that you want to support. So it's quite straightforward. But there is a lot of things to type, so that's one of the things that I don't like about it. So for memory representation, so you have the value object, pimple, that is hidden. And in the heap, you have the value with the VTBL, which contains all the specialized method to manipulate that object. So, advantages, which are very great, is you obtain polymorphism without inheritance, like duck typing. You have clear architectural boundaries inside your code. You introduce decoupling and dependency inversion. So it's easier for testing, for example. It can be easily customized and extended to new types. So those are great advantages if you need them. But most importantly, it breaks dependencies and you create system with good modular design in your code. So that is super important, I think. And if you want to have something that is easily maintainable, that's the way to go. Of course, there are problems. So runtime overhead, because you access everything through indirection, in fact. Of course, you erase the type, so you don't know what's inside your type erased value. Sometimes might be a problem. There's a lot of boilerplate. Of course, there is hidden dynamic allocation, which might not fit your case, your project. So last year I gave a talk about, I think, a nice framework to do type-erasure, and I will reuse that framework in this project. And I will show it how to use small object optimization within that framework in an easy way. So that framework has two flavors, the usual one, and there is another one where in the public object, so in the value, you still have the pimple to the erase value, but that is just for memory management, so deleting or cloning. And you have another pointer, so VTBL with all the function that you want to implement for that object. So the object takes twice the size on the stack, for example, but with this we obtain some performances, simply because we have only one interaction to actually manipulate the object. So in short, I will go quite quickly. So what's important for the following part of the talk. So we have a base class. That's the base class provided inside the library of my framework. So it takes as a first template parameter the VTBL, which is a structure defining all the fixed set of methods that you want to implement for all the objects. Visitor strategy, we are not going to speak about it today, but the pinball strategy, we are going to use it and change it. So the base class has, again, two members, a pointer to the implementation and a pointer to the VTBL. That's the constructor. So everything is passed to the pinball strategy to create a pinball and also to create the VTBL. So create the VTBL. So it takes the type of the value you are going to deal with. And it is one of the important parts is inside the pinball strategy, you have a template structure called cast value that the sole role is to take the pinball and obtain a reference to your object. And that's how the link is done. So for example, if you go back to the shape example, so for the shape, instead of writing all the code before, that can be something like 80 lines of code, you just have this screen. So the shape VTBL with two methods. So instead of drawing here, I took, for example, two methods, compute the area and compute the perimeters. The create static member, which will return a shape VTBL. So its role is to initialize the do area and do perimeter member with a lambda function. You can't do that because there is no, it's a lambda function without context. So static, and it's a context method, so it will run all the time. And then for the public object shape, you define it from the base of the framework. You define the constructor and the two methods that you are going to manipulate. So in short, it's much shorter, less boilerplate for the type erasure. Now, how can we improve this? So in this case, sorry. Okay. So we have the public object, we have the pinball and VTBL. The pinball point to the manage value, and the VTBL point to the VTBL structure. But for example, if the value is very small, like an integer, this part is like a waste of space. If you can store that integer, for example, in pinball, it will be much faster and efficient. We just need to adapt, of course, the VTBL. So to know that the value is not pointed to by the pinball, but directly in the value. And for our case, for the expression evaluator, for everything that cannot be stored inside the pinball directly, we still use the pinball as a pointer, but we use a memory arena that will handle all the values. So, and this is another, for our case, it was also another nice trick because we can put all the values together in the same memory object, so there will be aligned next one to each other. And for example, the memory arena is managed by the parser. So when the parser runs out, the memory arena is erased and all the values are erased. So it's fine as long as you keep the parser. So, and usually it's quite easy to do. So if we go back to the framework, so we have the pimple strategy here, the creation of DPTL. So again, that's where all the magic will happen. So we need to modify the cast-e to know that we are going to use a value inside the pimple instead of using the value pointed to by the pimple. So we need to do some magic there. So we can write our own pimple small object strategy. So in this case, we don't. I call it pimple SSO strategy no copy because we don't want to make copy of nodes. There is no point in the parser to make a copy of the node. Once it's created. Yeah, we will have no copy, but we want to move it, of course. Okay, so the pimple will be a type called pimple SSO. We don't want to clone. And that's the first part. So we create the pimple for the value t. We don't take the memory and for the when the small object optimization is on. So this is a concept that will turn on this function only if value t respects the criteria inside the concept. So we will see what is this concept, how this concept can be defined later. So that means that if you passing a type of value that cannot go in the people, this function will not be called or even defined. So, and that's great, because then the compiler knows exactly which branching he can optimize or not. So we create the pimple from SSO trial, create a pimple. Same for the non-small object optimization case, but in this case we are using the arena. Okay, and then here's the cast value. So the template type that do the link between the pimple and a reference to the value we are going to manipulate. So first we remove everything that is not useful within the type, so the constants and the volatile or any reference in it. So that is the function. It will take a const volume pointer and return a const ref to our value. So for this, we retrieve the pimple pointer from P, and we call SSO value. I will show it later how it is done, so I'm going backwards in the code. Same for the non-const function. For the small object optimization, we have the same value that is only defined if non-small object optimization concept is true. And it is how we got a pointer to the pimple. So in this case, for us, we simply cast the const void pointer into the const pimple. And that's not Ubino case because everything is clearly defined. So the two concepts. So, and I would say that's the core. So the first concept is small object optimization trivial. So we want to be able to do the SOO, small object optimization, if the type is trivially copyable, is trivially move constructible, and of course if it respects some alignment for the buffer in which it will be contained. So we must have the same, at least the same type of alignment or less, and it must fit inside the buffer. And for the non-SSO, it's just the opposite of the previous one. And now the pimple SSO structure. So that is the structure that will actually contain either a pointer to the object in the arena or the object inside the buffer. So we define the default constructor. We don't want copies. Here I define two types for tag dispatching, so to make sure that you are going to call the right constructor in the two cases. So that is a constructor when we use the arena, so we simply make sure that P inside the union is initialized with the pointer to the value coming from the arena. So that is the static method used before. And for the small object optimization, so again, we use the concept defined previously to make sure that this constructor is only available if the type that you want to construct meets the requirement of that concept. So we have the value, and we initialize it inside the buffer. And that's the static function that's just calling the previous constructor. So as you can see here, everything is well defined. Either it goes into some function because it meets the criteria of the concept, or it doesn't. So it's not possible to have some kind of misuse of the union, because it's either coming from the arena or it's coming directly from a type that can be put directly into the buffer member of the union. This is some pointer accessor. So to get a pointer to the value, but in void, and here we cast to a reference for the non-SSO value, and same for the SSO value. And here we have two functions, const and non-const. The get function that returns a void pointer to, in fact, in this case, this, so the pimple SSO structure. In fact, the get function here is the equivalent of the get function in the stud unique pointer. So it will get the address of how to manipulate the value. And the buffer, that's just for clarity, but it's just a buffer of car with some alignment that you want to have and some size. So, okay. So in fact, before, so for example, for a literal ST node containing 2, we will have a pimple and a VTBL. The pimple will point to the value 2. And after the SSO, but we have the 2 inside. And the VTBL has been is correctly updated just because it knows that the 2 is inside the pimple. So there is no switch or anything knowing, okay, am I in SSO mode or not? Everything is done at compile time. Same for a variable. So the pimple will point to some memory containing an address of X inside the context. And after, so we have the pointer inside the pimple pointing directly to X. I don't know if you have any question at this stage or already lost you. No? Okay. Yep. Okay, one step further. Okay, and in fact, we can go one step further. Sorry. Okay. So, for example, we have the operation x plus 2. So if we take the previous step, so we have x point directly in the pimple and 2 directly in the pimple. It would be nice, for example, if we take those two and we put them directly in the pimple for the plus operator. But this time the plus operator is a template structure that we know that on one side I have a pointer to the value x, and the other side I have the value 2 directly. But for this, of course, you need to have the pimple big enough to contain not one value, but 2 values. So if you increase the size of the pimple, you can do this type of things. So, and the plus operator, for example, so you define a binary operator, template binary operator function that takes first function a builder for the node, the type of operation that you want to apply, and the left-hand side and right-hand side node. You define the struct operation, so with all the possible combinations that you want to deal with. You have the operation for the integer, for the number, for the string, and for the list. Then the trick was here, because this binary operator template function is quite heavy to compile, because it needs to do a lot of data extraction. It needs to extract data from inside the people in case we have a literal, in case we have a value, or in other case, and it can be check if it can combine it into a compacted pimple. So you define an external template specialized function, and in the CPP you just specialize it. And so, after all of this, just a lot of work, we have those results. So for the same expression, so 3 times x plus 2, the row C++ expression, so 3.2. The OO, it was 7 times slower. And now temperature erasure plus small object optimization, we have 3.8, so 1.2, factor 1.2, which is nice. And for expert TK, again, it's more or less a factor of 1. So I was quite happy with it. And for more complex expression, we have those results. So our method is 3 times slower. Expert TK is about 2 times slower. So there is still some improvement, space for improvement, but I didn't have the time to do that. Yes. So doing this work, what did we do? So we support some common mathematical operation and function. We support some logical expression. We support string, so concatenation of strings, also finding things in string, taking substrings, check if a string contains another string. We can split a string into a list and other type, convert string to date, and back and forth. We support list operations, so concatenate string, check if an element is inside the string, not inside the string, take some element or slices. We can join string list into a string. We manipulate date and time. And we also introduce something quite simple, so as a low-hanging fruit, so it's constant simplification. So for example, in one part of your AST tree, everything is constant. You can evaluate it directly. And so you just erase one part of your AST tree by replace it by a literal, which will be the computed value. And of course, we learn about small object optimization in this case. And so, yes, all these things, in fact, we found it is sufficiently efficient for a purpose. And in fact, it can be extended quite easily because we can add additional function, additional type in the parser. And so for us, that was very important because we have customers that are very creative and we want to support their needs. So, conclusion. Of course, this is one more expression evaluator. There is many available. This one required a lot of iteration. I didn't have enough time as I wanted to go as deep as I wanted in all of these iterations, and this talk is the result of this work. And I would say, when you have an idea, always do some benchmark to know if you go in the right direction. So again, I learned about small object optimization, and then I still have more ideas to test and maybe implement and go further in this framework. So I thank you, and if you have any question, we'll be happy to answer them.
A small question here. It's about the concept you have there. It was trivially copyable, right? And
yes.
Is trivially move constructible. Yes. My understanding of this, I might be wrong here, but my understanding of is trivially copyable means that it's trivially copy constructible and trivially move copy assignable. Is there a sane place where the trivially copyable would be true, but the trivially move constructible would not be true?
I don't think so, but I like to be on the safe side.
All right. Okay. Thank you.
Don't think so, no, but it doesn't cost anything here to add it, just to be very explicit.
Hi. On the last results, expert-tk, that's how it's called, right? The other library was still faster. Do you know how they are faster still?
Can you repeat? Sorry, I missed the...
There was a third library, it's called like
yes.
expert-tk.
Yes.
Do you know what do they do to still be faster than type-erasure plus SSO?
I'm pretty sure I didn't have the time to dig in their code. Because it's quite long and I don't have enough time on my hands, unfortunately. But I have the impression that they also managed to pack together not only 2 operations, but 3 operations. So, for example, 1 addition and then a multiplication, or vice versa, inside together. Because they also have a shift. For example, the measurement they do from 0.3 to 0.6, and then if I continue, it's 0.9, so they do also a jump. And that difference, 0.3 to 0.6, is, as I did some simulation, is always an indirection. I can simulate that by having an indirection into the AST tree.
I see, thanks.
You're welcome.
No more questions? Okay. Online? Anything? Okay. Thank you.
Thank you.